All right. Well, welcome. We didn't meet in person last week, both because we had agreed in advance that we were going to do that one electronically, but then as it turned out, it was a bad weather event, and so they canceled classes anyway. So I don't know who came out ahead. But I'm glad that we were able to keep moving, and tentatively it's looking like next week we could do that one online as well. So in the past you mentioned that that was helpful for you because then it saves you the round trip.
Much better.
And then it also allows you to go over the material at any time that's convenient. So I think we're going to try for the same thing again. But I will, I'll send out an announcement and a link to the lecture when that's all been finalized.
So are you going to teach the class 3 again?
No, class 3, the video's online, and if you have questions, I invited you to stop by and ask me questions. You know, if you're having trouble with the program, I have lots of office hours, and I'd be happy to go over it with you, but I'm not going to teach the lecture a second time.
All right.
Today what we're going to talk about is water surface profiles. And I'm just curious, have either of you had experience before with HEC-RAS? Have you used HEC-RAS before, the software? Have you used it, HEC-RAS?
No.
Okay. Well, I'm glad actually that you're both on the same page, because sometimes the challenge is when one or two students in the class have used it extensively, like they use it a lot at the Army Corps of Engineers, and so occasionally we'll get some people who know a lot about HEC-RAS and then they're not quite so happy when we go over the basics with people who haven't been exposed. So it's good that we're on the same page about it. So this is a picture that I pulled off the internet today just to illustrate the idea of, we sometimes think of rivers as being static and that the flow rates are some fixed volume. Of course, we know that's not the case. If you drive by the Ohio River very often, you know that from time to time the water levels can rise and fall quite a lot. In fact, I was just on a walk down at Harris Riverfront Park yesterday, and there was mud all over a lot of the walkways and the boat ramp because the water level, anytime it's high, it takes and deposits muddy silt sediments, and then when the water level lowers, then it's all exposed. And so I think the water levels were much higher over the last few days, and we'll look at a gauging station for the Ohio River, and I think it's going to show the same thing, that water levels were high within the last week, but now they're a little lower. So here in this, you can see that if the water levels are higher, it's kind of obvious what is going to be submerged next. There's a bank on this side that has some rocks. There's also some exposed rocks on this side of the bank, and so as the water level continues to get deeper, think about what would be submerged. And so this is going around a bend, and this floodplain area would likely be submerged. Now it's up against a hill though, and so the water level would have to get pretty high before it starts to get up against this hill. And so what we're going to focus on today is some numerical methods for calculating what's the water depth when there's a certain flow rate. And you've already had some exposure to this with the work we did in HY8. You know, HY8 is an open channel calculator that specifically focuses on culverts. HEC-RAS is a more sophisticated open channel calculator that can handle all sorts of complications that HY8 isn't able to accommodate. So that's kind of where we're heading with today. And the reason why we need numerical methods to predict what the flow is going to be is that it's pretty uncommon to have a lot of river depth gauging stations. Here in the state of West Virginia, there are less than 100 locations where they're actively measuring the depth of the water as a function of time. So we'll look at the gauging station for the Ohio River at Huntington, West Virginia. But besides that gauging station, there are less than 100 others in the state. And if you think about how many places there are water, how many creeks, how many streams, how many rivers are there, and so there's many hundreds of important water bodies where we'd be interested, and there's lots of cities along those water bodies. And so at any particular location where construction is being planned or where someone's trying to build a house, we can't measure it directly, so we have to have some way to predict what the flow might be. And so a gauging station allows you to have that direct measurement of flow, and we sometimes are able to use historical measurements of flow and combine it with a numerical model to predict what the depth would be under different circumstances. So for instance, if we know what the water depth in Huntington is when there's a flow rate of 10,000 cubic feet per second, then we can use that as a starting point for predicting what would the depth be when there's 15,000 cubic feet per second. So on the subject of historical data, here is the last 7 days of flow data at the Ohio River at Huntington, West Virginia. So the USGS, the United States Geological Survey, is who operates and kind of maintains the database of all these gauging stations across the country. You can see that there is a station number that refers to the Ohio River at Huntington, West Virginia. And then if we scroll down, you can download or visualize a lot of different data. But for our purposes, this is showing over the last couple of days. So here's January 30th through February 6th. And this is the gauge height in feet. And so it's rainy today. And what we see is that the water depth is increasing in response to the rain. But what I noticed when I was walking around on the boat ramp and the walkways by the park is that when the water levels were up here, parts of the park were submerged that aren't submerged when I went on my walk yesterday. And so all that mud and deposition and silt and sediment that had accumulated was because of the variable depth over time. So this is just an instance of one location, and there's lots of different ways to download and visualize that data. But what I want to compare and contrast is the infrequency of having physical measurements with the number of places that we need to know how deep the water is going to be. Every person who lives in a house wants to know when it gets really rainy, how deep is the water going to be here? And in fact, it can have a huge effect on the value of your home. It can have a big effect on the flood insurance rates that you pay, your adjacency to a location that may be flooded. And so what we're going to take a look at is some ways to calculate that. When I teach hydraulic engineering, I teach my students in that course a variety of different ways to calculate depth. And one of those approaches is the standard step method. And this is the method that's used by HEC-RAS. And so what we're going to do is we're going to work an example manually, and I'm going to show you basically what's the calculation procedure, and then we're going to do it with HEC-RAS. So I never think you should use software that you don't understand. You should always know what are the calculations going on in the background, have an idea of the fundamentals, because you can really get into trouble if you don't understand what calculations are being automated and what the assumptions are. And so that's why we're going to do this manual calculations with the standard step method first. So what we're going to determine, this method is used to determine an unknown depth at some location that we're interested in. And the nice thing about the standard step method, in contrast to other approaches that are out there, is that the standard step method allows for a cross-sectional shape to be changed. So some cross-sections, some channels are very simple and prismatic, which means that at one location and then another location downstream, maybe they have the same top width, maybe they have the same bottom width, and it's pretty easy to do calculations relating to water surface profiles when the channel isn't changing its dimensions. But think about an actual natural channel. And let's in fact go back to that first cross-section. So here at one location the channel may be narrow with some faster moving water. Downstream the channel may be wide with slower moving water. And between those sections, the slope can be changing as well. So natural channels are highly variable. And so we need the standard step method because it may be that instead of this downstream, upstream, that's really predictable and regular, it might be that in a natural channel, we've got one section that is relatively wide and another that's relatively narrow. And so how we calculate the water depth responding to changes in cross-section is best accommodated with the standard step method. So the energy equation. Do you remember the energy equation from fluid mechanics or hydraulic engineering? There's two different versions of it. One is in terms of pressurized pipe flow, and then the other version of the energy equation is for open channel flow, when we have a depth rather than a pressure. So if we rearrange the energy equation, generally what I would do is I would write the energy equation as y1 plus z1 plus v1 squared divided by 2g is equal to y2 plus z2 plus v2 squared divided by 2g. This is the energy equation assuming no head losses, but then if there are head losses, then we account for them on the right side. So head losses. And head losses may be frictional losses due to the resistance of flow from the surface, or it could be expansion and contraction. So here, this equation that I'm showing you, this formula, is combining together the elevation term and the water depth term into just what we call the water surface. And so this diagram, what you see in the picture is water flowing downstream in a channel. So the water is going from left to right, and we're kind of keeping track of what's going on at two locations. Here at location 2 is upstream, location 1 is downstream. And I give you this little warning here that 1 and 2 refer to known and unknown when you're using the standard step method. When we use just the general version of the energy equation, we usually assume that 1 is the upstream location and 2 is the downstream location. But here, in the standard step method, what we use is where we know what the depth is, we say that's location 1, but then location 2 is where we don't know the depth. So most of the time we'll solve the standard step method for subcritical flow conditions, meaning that the water is relatively slow moving, and so that's the example, and the homework assignment I have for you is related to subcritical flow. Okay, so if you compare the energy upstream and downstream, we look and see that there's the overall water surface is measured from some elevation datum up to the physical height of the water. So that's WS2. And WS2 is both from the datum to the bottom of the channel, so that's Z2, and then from the bottom of the channel up to the water surface, that's Y2. And then above that, up to the energy grade line, is the velocity head, V2 squared divided by 2g. And alpha is just a kinetic energy correction factor that will approximate as being close enough to 1 that sometimes we don't even bother including the alpha in the rest of our calculations. So as the water moves downstream, it's losing some energy, H sub L. H sub L is the head losses that are due to frictional interaction with the bottom of the channel. So the water, as it moves to the right, is experiencing some shear stress. The soil or gravel or whatever the channel is pushing the opposite direction from the water's flow, and that causes a head loss. So what this equation is saying is that the amount of energy at the known location plus the losses encountered as the water flows from one point to another is equal to the total energy at another location. So the total energy being the water surface and the elevation head. Excuse me, the water surface and the velocity head. Now I know this seems pretty abstract, but I've put together a spreadsheet template that we're going to use to go through the process of solving the standard set method. So the starting point in a question like this is, if we know the depth at 1, how deep is the water at 2? That's what we're trying to find out. You know, for a certain flow rate, for a certain channel material, meaning maybe it's concrete, maybe it's sand, maybe it's cobblestone rock. For a certain distance upstream, this L, how deep is the water going to be? And so what we have to do to solve the question, how deep is the water at this location where we don't know the depth, we start with a guess. And the reason why is that there's too many unknowns to calculate it directly. We have to begin with a guess of what is the water surface elevation at location 2. And then we check that guess by calculating a bunch of factors and see if everything balances out. See if there's a balance in the continuity equation and the energy equation. So what we're going to do is, with this guess of what the depth is at 2, then we'll find out, well, what does that mean about how much head loss there is, the observed head loss, if the depth is a certain thing at location 2. And then what we do is we calculate what would be the actual head loss for those flow conditions based on the slope of the energy grade line, which is related to friction. And this S sub F equation here is just rearranging the Manning's equation. So we're solving the Manning's equation for the slope. And Manning's equation is what relates friction factors, which are N values, to the flow rate and channel geometry. So this first term is energy loss. The second term is related to whether the channel is getting wider or narrower. And so these are local losses related to contractions and expansions in the channel. So then we compare these two, and we know that they should be equal, that the observed and calculated head losses should be equal. And if they're not, then what we can do is we can update our estimate of what the guess depth was. And so we'll go through a process of calculating an updated guess of the depth using this standard step equation, and then correcting with this updated guess by averaging our first guess and the new guess. And by averaging the two, then what it does is it gets a little bit closer to the correct answer. It converges through different repetitions. If you repeat the process several times, then eventually it will converge on the right answer. All right, so here's what we're going to do. I know that if I said apply these equations, probably you wouldn't know where to start. And so I think one of the ways that we can learn how to start is with an example and with the template file that I've provided. You're able to connect to MU Online, right? Yes. All right. So you go to MU Online, and there's an Excel file right on our class page. If we go to our class page here, MU Online. It's at the bottom of our front page here, standard step, student start file. And just download that. And then when you've got it, go ahead and open it up. Once you've got the template, we'll take a look at the example and what it's asking. All right, so here's our example. What it's asking is, we know that the water depth is 5 feet at this location. And we want to find out how deep is the water going to be upstream. And you'll notice that we're measuring elevations according to some datum. Invert means bottom. So they're saying the bottom of section 1 is at an elevation of 5 feet. And right now, with 1,000 CFS going through it, we measured that the depth is 5 feet. So if we go 1,000 feet upstream of section 1, now the channel is no longer trapezoidal. Now the channel is rectangular. And so we want to know what's the depth. And so this is pretty complicated because not only are we going upstream, but also the channel is changing its shape. It's making a gradual transition. Those sides are coming up gradually, and then it just reaches the rectangular cross section at 1,000 feet upstream. So let's begin by going over some calculations on the board, maybe some of the preliminary stuff that we'd be able to do even before switching over to the computer. I'm going to switch off the monitor and try and bring up my... All right, so we've got this, at the place where we know what's going on, it is a trapezoidal channel. And the side slopes are such that the depth is 5 feet, and then it's 2 horizontal for each 1 vertical. And so what that means is that if the depth is 5 feet and the bottom of the channel is 25 feet, that's just the bottom of the trapezoidal channel, we are interested to know what's the top width. And so if it's a 2-to-1 side slope, then that means that on the sides here it's going to be 10 on the left, 10 on the right, and 25 across the top for the rectangular section. So that's just because of the side slope. For every 1 vertical, we have 2 horizontal. All right. The other thing is we know that over the course of a distance of 1,000 feet, how much does the elevation change from the upstream to the downstream section? The given information, I think it's there on your notes. It says the invert is 5 feet at section 1 and 7 feet at section 2. So it's just increasing by 2 feet. So the delta Z is 2 feet. And we use that to get the slope of the channel. And so the slope, how steep the channel is 2 feet out of 1,000. And so 0.002 is the channel slope. Okay, normal depth. Normal depth can be found from substituting into the Manning's equation, Q equals 1.49 for traditional units, times area to the 5/3 power divided by n, and the wetted perimeter to the 2/3 power, the slope to the 1/2. So here we could put in the flow rate that we know. The given flow rate is 1,000 cubic feet per second. So we can put in the given flow rate, the given n value. On this example, we're told that the n value, or however rough this material is 0.05. And then the area, the cross-sectional area, would be 25 times the depth plus 2 times y squared, and the wetted perimeter is 25 plus 4.472y, because what we would do is here, the length of this surface is going to be the square root of the height and the depth combined. And so the point is there's some formula where the only unknown is y, and that's the normal depth, And so through Manning's equation, we can find out that the normal depth is 6.848 feet. But in our example, we're told that the flow happens to be only 5 feet at section 1. So what that probably means is that the water is approaching some sort of either a change in slope or a drop-off. You know, just to exaggerate things, we're going to say let's assume it's approaching a drop-off. So there's some location where the depth that we see is 5 feet. But if we went further upstream, then the water's going to be getting deeper. And so we want to find out, if we go 1,000 feet upstream, how deep is the water going to be at that location, at that upstream location? Another way to look at this, whether conditions are subcritical or supercritical, we kind of have to assess whether the flow conditions are subcritical or supercritical because the direction that we do our calculations are different in the standard step method. And so there's a function called the Froude number. And the Froude number is the flow rate squared times the top width divided by G and A to the third power. So, and all of that's to the 1/2. So our top width of the channel at the location where the flow depth is 5 feet, our overall T is 45 because it was the 10, the 25, and the 10 on the other side as well. So to calculate the Froude number, what we do is we substitute in the flow rate. So 1,000 CFS squared times the top width of 45 feet divided by G, 32.2, and the 175 feet squared is the cross-sectional area at the conditions that we have. So if we substitute in when y is 5, then that gives us a cross-sectional area of 175 feet squared to the 1/2 power. So the Froude number in this instance is going to be 0.51. And anytime the Froude number is less than 1, that means it's subcritical flow. So HEC-RAS will assess that automatically, but in our case, we're going to just double check it because that affects how we use the spreadsheet. So we know it's subcritical conditions, and so if we go back to the slides, the reason why that's significant is that if we have subcritical flow, then the known section is downstream and we're working upstream. So that is the case in this example. In this example, downstream where we know the depth is 5 feet, and we want to find out how deep is the water upstream where it's a rectangular channel. We don't know how deep it's going to be, but we do know the width of the channel is 25 feet at that location. What would be your guess? Do you think that the water depth is going to be more than 5 feet at section 2 or less? When what's happening is, look at the bottom width. The bottom width is the same. It's like we've got some concrete channel, and it's getting like the sides are coming up. And so you think it's going to be deeper. What's your suspicion there? Why is that?
Because where you're pushing in, you're pushing the same volume in on itself. This one.
Right. Yeah, there's less flow area,
Right.
less conveyance, as they call it in the parlance of HEC-RAS. Is, you know, the area that's available for flow is a function of the conveyance. And so if you reduce the flow area, then the water depth has to increase if the slope is the same and the flow rate is the same. All right, so you've each got that spreadsheet file. Let's begin with that. What we're going to do is we've got all of the equations that we need from that method that I stepped you through. And let's put in the given information. For the conditions that are explained in the in the example, our flow rate is 1,000 CFS. Okay, the N value, the roughness of the material is 0.05. The Z1, let's go back to, oh, here's the sketch right here. So Z1 is asking how far above the datum is the bottom of the channel at section 1. So we put in 5 there. And what should we put in for the elevation of the bottom of the channel at 2? 7, right? So that's from the drawing, 7. Now C is a factor related to how much energy is lost at expansions and contractions. And a rule of thumb is that you might have an expansion or contraction coefficient around 0.3. So let's use that. We have a contraction. Let's say it's 0.3. And then the distance between these two sections from 1 to 2 is 1,000 feet apart. All right. Now, the order of all of this stuff, like the column order, kind of implies the workflow. We're going to work from left to right, and then we're going to check the validity of our guesses, and that'll tell us what to do for the next iteration. Okay, so at location 1, we know that the water depth is 5 feet deep, and so the cross-sectional area of that water depth, we're going to use the equation I wrote on the board, where it's 25y plus 2y squared for the cross-sectional area. So equals 25 times the depth plus 2 times the depth, A30, and that's squared. Okay. So the cross-sectional area 175. I guess we could have just typed that in because it was solved for on the whiteboard somewhere. I have it, yeah, cross-sectional area down in the Froude number. Okay. So velocity. Remember, Q equals VA, and so A1 times V1 is equal to Q1. The other way of solving that is V is Q divided by the area. So here we want to know how fast, like what velocity is the water traveling at section 1. So that is the flow rate, Q, and then I'm going to type the F4 button to put in those $ anchorings that's required to have it always look in the same spot. So B21 divided by the cross-sectional area. And the answer should be 5.714. So is everybody with me so far? All right. Wetted perimeter, let's use that equation that's up on the whiteboard again. So it's 25 plus 4.472 times whatever the depth is. So our wetted perimeter should be 47.36. And what that's talking about, wetted perimeter is the distance that the water is in contact with.
So you said 25 plus 4.472 times what?
Times the depth, y.
Okay.
Yep. Okay. Hydraulic radius, R sub h, is the area divided by the wetted perimeter. That's the definition of hydraulic radius. Okay, so for that you should have 3.695. All right, now E sub 1 is asking how much energy is there at 1? And this is the equation we're going to use to calculate the energy. It's going to be the depth, the elevation above the datum, and the velocity head. Okay, so energy is the Z, so the distance from the datum up to the channel bottom. So that's 5 plus, actually, let's, rather than me typing it in, let's just click up here because we have the Z1, right? So Z1 anchored, plus the y at that location plus, now we need velocity head. And so we have the velocity, so I'm going to say v squared divided by 2 times g. And in traditional units, g is 32.2 feet per second squared. Okay, so the total energy at 1 should be 10.507 feet. All right? So now we use this equation to find out the slope of the energy grade line at location 1. Okay, so this is just the Manning's equation rearranged in terms of finding an unknown slope of the energy grade line. So equals, okay, so n, anchor that reference, times q, anchor that reference, divided by 1.49 times the area, which we calculated already, times the hydraulic radius, which we calculated already. And the hydraulic radius is to the power of 2/3. So to the power of 0.666667. So that's to the 2/3 power. And then I close parentheses. And then I close parentheses one more time and square it. Sometimes it's tricky to translate these equations into where all the parentheses need to be with Excel. But it's a good skill to have. Okay, so the slope of the energy grade line at location 1 is 0.00644. Did you get the same thing?
Yeah.
All right. Did you get it? All right. So now we have to just make a guess about how deep the water is upstream. Now we already know it's going to be a little bit deeper than the 5 feet that we've got. But let's just say that we didn't want to use logic. We'll just say, well, what if it's the same depth? So I'm going to start with a guess of 5 feet is the water depth. Okay. The water surface at 2, remember the water surface is defined as the elevation and the depth. And so it's going to be the depth plus Z2. And I'm going to anchor that reference to Z2 so that it always looks where we have that 7-foot depth. Cross-sectional area in section 2 isn't trapezoidal. It's just based on a rectangular channel. And so the cross-sectional area at 2 is going to be 25 feet wide times whatever the depth is. So let's do 25 times the water depth. Okay, so now we know if the water depth is 5, then we'd have this cross-sectional area, and therefore we can calculate the velocity, because that is Q divided by the area. So it should be 8 feet per second if the water depth is 5 feet. Okay, we still have all these contingencies that we need to determine, like if the water depth is that, then tell us all of the characteristics of the flow at section 2. So the wetted perimeter would just be the bottom width of 25 feet plus 2 times the depth, since we'd be in contact with the channel in both of the sides, on the left and on the right. So the wetted perimeter is 25 plus 2 times the depth. The bottom width, 2 times the depth is for the left and for the right. So the wetted perimeter then would be 35, and hydraulic radius again, that is area divided by wetted perimeter. All right, so then the energy, the definition of energy is the depth, the height above the channel bottom, and the velocity head. So both these first two parameters, z and y, both of those are included in the water surface. So what I'm going to say is it is the water surface plus, now we need to do the velocity head again. So v squared divided by 2 times 32.2 divided by 2g. So we're going to find out how much energy there is at location 2. And we should get that if the water was that deep, then there would be 12.994 feet of total energy at that upstream location. All right, so next we again use Manning's equation to calculate the slope of the energy grade line if we have this much energy and the channel geometry that's already been described. So it's the n value, anchor the reference with F4, times the flow rate. Again, we have to anchor that reference, otherwise things are going to screw up later on. Divided by 1.49 times the cross-sectional area times the hydraulic radius to the power of 0.666667. Oh, that's not to the power of. To the power of. All right. And then we close that parentheses. We've got one more parentheses to close, and we square it. So if you've keyed in the equation correctly, then the slope will be 0.0132.
So the M30 is raised to the power
of, yeah, 0.6667. And then you close the parentheses twice, and then you square everything. What we should get is 0.0132. Got it? No? Let's take a look at your equation. You need to put another parentheses around this. Otherwise, it's only dividing by the 1.49. So it's this.
Right.
Okay, so now observed head loss is the difference in the energies. So E2 minus E1. So what this says is that there's 2.487 feet of loss if the depth upstream is 5. And now the SF bar, the slope, the average slope of the energy grade line, what we're going to do is we're going to take the average of these two values, and that's telling us the average slope between the two sections. And so it's equals this plus that divided by 2. That'll give us the average slope of the energy grade line.
Can you pull that equation up again? Sorry.
Pardon?
Can you show
Oh,
that?
sure. Yep. So we're just taking the average of the two energy grade line slopes from before. You got it?
Yeah. Okay.
And
I
then,
got 0.0098120.
that's fine. It's probably just the amount of precision you're showing.
Okay.
Yeah, so if I,
Got 20.
I mean, if you round it, you can pull it out to be different.
okay. Okay, head loss calculated, we use this formula for our calculated head loss. Okay, so equals this average slope of the energy grade line that we just determined in the previous step times the distance between the 2 points. So L is how far apart section 1 and section 2 are. And let's anchor that reference with the dollar sign. Okay, so the head loss is due to frictional losses and also losses related to expansion and contraction. So here now, the C value times the velocity head at 2 minus the velocity head at 1. So that's going to be the velocity head at 2 is V2 squared divided by 2 times 32.2 plus, minus the velocity at 1 squared divided by 2 times 32.2. And I think I might need to, let's see. Oh, that's good. All right. So what we're looking for the calculated head loss is going to be 9.967. Roughly, depending on how many 6s we put in that exponent when it was to the 2/3 power. Okay.
.966.
Good. That's right. All right. So now, water surface calculated. This is what we assumed. We assumed that the water surface at location 2 would be at an elevation of 12. But now what we want to find out is, based on all of our assumptions about energy losses, what is the actual calculated depth of the water there? And so we're just rearranging the energy equation, and we're kind of subtracting out the head losses. So it is water surface 1, which we have, the water surface is,
0.006.
no, water surface 1 is the depth and the elevation above the datum. So water surface 1, what we need to do is have y1 plus z1. And that's what gives us water surface at 1. Plus the velocity head at 1. So now we're doing v1 squared divided by 2 times 32.2. Plus the calculated head loss that we just did. Now we're not going to be able to click on the location because it's centering on top of where that is, but we can type it in. It's C30. Okay, so that's plus the head loss, and then minus the velocity head at 2. And so that's minus v2 squared divided by 2g. Now the good news is that it's going to get a lot easier. You see that there's so many rows on this spreadsheet. We're not going to have to type the formulas in for each one of those rows, because once we get the spreadsheet functioning, we can click and drag and it will correct the calculations and iterate in kind of an automated way. Okay, so the number that we're looking for there is 19.48. So we're saying that we assume that the water surface elevation up there at location 2 should be 19.48 if we have all of these losses that we know about. But oh yeah, we had 12. We already had the water surface from before, right? So compare it. Our original estimate was 12, but when we consider the energy equation, it's saying, no, it's more like 19. So what we do is we split the difference. This updated is going to be the average of the two. So the updated water surface is our initial guess of 12 plus this updated guess of 19 divided by 2. And so we've split the difference now. We have an updated guess of what the water surface might be. And just so that we can keep track of how close things are getting, let's calculate the percent difference between our initial guess and the updated one. So the percent difference is equals the updated minus the initial divided by the updated times 100. So that'll give us the percent difference. And the reason why we're calculating the percent difference is we know that our solution is converged once the percent difference is less than 1%. So we're not there yet. Right now our percent difference is 23%. But what we'll see is it gets much closer to 0. All right, so any questions so far, either about specific calculations or maybe the overview of what's happening? The overview is we make a guess and we see what does the energy equation say about that. And then we compare what the energy equation dictates the depth would be with our guess and make an improvement. Okay, here is the known section. And all of these known values, if we drag it down, you can drag that all the way down, and there's one more thing. The known depth is going to stay as 5, but okay, just click down, and then we're going to have to override just this one. It stays as 5. Everything else will calculate correctly and automatically. So do we have this filled in? Did yours go 5, 6, 7, 8 on the left?
No, I was doing the percentage difference.
Ah, okay.
So highlight it to...
Yeah, highlight the top row
and drag it down.
and then just drag it down. What we will have to do is override that left because it thinks that it's counting. So if we change it to 5 for all of them, since it's the known section, nothing is changing at location 1. You need to use the dollar signs here because we always want it to look up at, we always want it to look up at here for the Q. So if you put in, do you know about anchoring the dollar signs?
No.
Have you been putting those in?
No.
Okay. You're going to have to change a lot then. Any of these references up here need to have the dollar signs in front of them so that it always looks here instead of the next one below.
Okay.
Yeah, so we did it to that one. Let's see, where else? Anytime we have a reference below
lower than 26. Okay, so this, for instance, you're going to need to anchor that. And the way that I do it is function F4, and it automatically puts them in. And then this is a reference to one of those, so function F4 there. Here, this needs to have the dollar signs in there. And if they're not there, then it's not going to work what we're going to do next. Here, F4 there. There. You see what I'm doing, right? All right, and then finally the average of 2. All right, so I think it should be set for what we want to do now. What we want to do next is have a better guess. This guess of 5 wasn't a very good guess. But what we can do is we can use this to come up with a better guess. And so remember that the definition of water surface is Z and Y. So therefore, Y is the water surface minus Z2. And we need to put in the dollar signs so that it's always looking up there. So what that means is, like, if the depth is 15.74, I'm sorry, if the water surface elevation is 15.74, then that means that the water depth is 8.74. Okay? So now what we can do, this is the nice part, is we can just highlight all of these, including the percent difference, and drag it down. And what it does is it calculates everything based on this better guess, and you'll notice that the updated and the original they're pretty close now, and our percent difference is only 3.5%. So our guess improved. And so that if we do it again, we can highlight all of it and drag it down again. Let's do it 3 times. And I'll calculate the percent difference. And it's not changing anymore. From iteration to iteration, if I continue, another 3, then it converges, which means that the answer isn't changing anymore. So what we know is that the water depth is going to be 8 feet. And the water surface elevation will be 15 at that location upstream. Okay? So do you have these same values as me? 8? No?
So the negative figure doesn't matter?
No. That just means that one of the guesses was smaller than the other. All right, so what did the question ask? The question asked is, what is the depth 1,000 feet upstream? So the depth here at section 1 is 5 feet. What this solution tells us is upstream the water depth is going to be 8 feet. And the water surface elevation is 15. So that's the manual way. And what we just did would be really hard to do for a river. Think about how complicated a river is, and it's constantly changing width, and the bottom is irregular. We only had 2 sections here, and we assumed a perfect transition between the two.
And so HEC-RAS is a way for us to use those same calculations, like the math behind it is the same, but HEC-RAS is automated and iterative, and so we can use the standard step method in a much more user-friendly way. So what you put into HEC-RAS is the flow rate and the depth at a certain location, like we just did. You put in the channel geometry, meaning how wide is the bottom, channel characteristics, like what is the roughness of the surface, and then any other information that may be relevant, like if there's bridges or if there are spillways or dams that are regulating the flow. Now, so it's really nice. Easier excuse me, easier to set up than the spreadsheet, but it has limitations, and one of the limitations is that it's just what's called a one-dimensional model, which means that really it's blind to what's happening side to side. If you're going around a bend, sometimes a river will have super elevation, so it'll be angled on one side compared to the other. And HEC-RAS doesn't account for those effects. Also, its performance for unsteady flow is described as unstable. Like it can do quasi unsteady flow, but it struggles. All right, so let's do that same example with HEC-RAS. It's going to be easier, although the first time you use the program, it's not a lot easier, it's a little easier. So let's go through that together. So start HEC-RAS if you have it available. We agree to the privacy policy or whatever. I'm not going to install the example projects. I don't need those. All right, so the program has a ribbon across the top that you kind of follow in the order from left to right. The first thing we're going to do is create this file. So create a new project and browse to a spot that you're going to be able to find your file later. So I'm going to call this 670 HEC-RAS example. And you'll notice that it's also giving that a .prj extension. That means it's a project file. So we're creating a new project, click OK, OK, and then you can see here in the kind of directory that we have the project name and the project file that we're going to be creating. So feel free to interrupt me at any time if there's an error or if you need to clarify. Otherwise, I'm just going to continue. So what we do is we're going to create a geometry that summarizes what we're looking at. And so we're going to do view/edit geometric data. And when you click on that button, it's going to bring up this window. So click on view/edit geometric data. And then we have this window. The first thing we have to do is, this is going to be a top view of the river. And we're only going to have 2 locations that we start with. And so when you click on river reach, it brings up like a pencil. So do 1 click, and then as you're dragging it across, we're going to stop with a double click. So we're going to terminate with a double click, and then it's going to ask you to name the river. So I'm going to call this example river. And then reach, a reach means like a section of a river. And so I'm going to call this the reach. And so we're on the example river, and the reach we're working with is just, the names don't matter so much. All right. The next thing that we need to do is tell it about the channel geometry. So we're going to create both the trapezoidal section and that rectangular section. And so we're going to click on cross sections, and we need to create 2 cross sections because we have one that's trapezoidal and one that's rectangular. So does everybody have this cross section data window up? All right. So click on add a new cross section, and then we're going to have 0 be the station for that. That's our downstream station. And we'll do another one, so add a new cross section at 1,000. So if you look at this list for the river stations, we've got 1 at 0 and 1 at 1,000. Now what we want to do at 0 is define the geometry of this trapezoidal shape. And so
I lost you on add the cross sections where you add the 0 and 1,000. What was that button at? Options.
Options, add a new cross section. So we're going to do 1 at 0 and 1 at 1,000. You got okay?
Yeah, good.
All right. So the coordinates. Think of its XY coordinates. The edge of this trapezoidal channel is at an elevation of 10. What I'm going to do is just type in station 0 is the how far over to the side we are, elevation 10, and then here we have station 10, elevation 5, station 35, elevation 5, and then station 45, 10. So that is the coordinates of each one of these edges. The top, the bottom, and then again at the top. Does that make sense? XY coordinates? Okay, so what else do we need to tell it about? We need to tell it how far apart it is from section 1 to section 2. So let's type in 1,000 for all 3 of those. LOB means the left of bank, channel is in the middle of the channel, ROB is right of bank. So you can do irregular cross sections that would have different lengths, but we're just going to put in 1,000 for all of them. And then the N values, we're given that the N value is 0.05, and we'll apply that to the left, center, and right. 0.05, 0.05, 0.05. Okay. We also have to tell it what's the left bank station is 0, and the right bank station is 45. So we're defining the edges of the channel. And then our contraction coefficient that we used in the example so far was 0.3. So put that 0.3 in for the contraction as well. Okay, and when you click on Apply Data, it's going to...
The expression remains the same?
Yeah.
Oh.
Click Apply Data, and it's going to create like a little trapezoid. It's not to scale, but it's a trapezoid, and we can see that the bottom of the channel is at elevation 5, the top of the channel is at elevation 10, and so everything seems to be as we'd expect. So now let's move from river station 0 to river station 1,000. And we'll put in the geometry there. So it is 0 for the X. And let's say that we're not sure how deep the water is going to get, so we want it to be nice and tall on the edges there so that it can contain all of the flow. So let's use elevation of 17. That's just saying that it's 10 feet above the invert. You know, the side walls are 10 feet deep. So 0 and 17, 0 and 7 defines the bottom. And then 25 and 7. So 25 is the width, 7 is the bottom of the channel, and 25 and 17. So if we click Apply Data, then it's creating a rectangular shape for our water to flow through. We're basically just defining, like, what does that conduit look like? And we can put in 1,000 feet for the next reach. and it copied over the end value, so that's good. We have to define the station, so the edges of this channel is 0 and 25. And then we want to, again, change that contraction from 0.1, let's make it 0.3. And then apply the data. Now, one of the ways that HEC-RAS is really powerful, we can close this. One of the ways that it's really powerful is it allows you to interpolate cross sections, because right now we only have 2 cross sections. We'll have more accuracy if we break that up into smaller pieces. You know, we're going 1,000 feet in just a single step. But if we do here the interpolation, let's see, where do I find that? Tools, XC interpolation, and we're going to do it between 2 cross sections. So we're still in the geometric data window, the tools menu, cross-section interpolation, and between 2 cross sections. So let's have it be so that our cross sections are 100 feet apart instead of 1,000. So the maximum distance between cross sections should be 100 feet. And then if you click interpolate cross sections, you can see, you can kind of get a sense for, you know, it's a trapezoidal, and now it's kind of like tapering up till it's rectangular. And this is going to give us more accuracy if it's calculating between each step, and each step is more gradual, rather than having it just be in a single step going from trapezoidal and instantly rectangular. This is a more smooth transition, and it'll give us more accuracy. So Zach, did you get it to interpolate the cross sections okay?
Not yet.
It seems like we have an error. Let's go in here and that's right. I think we're at 0 though. I think 0 might be where the mistake is. Yeah. All right. So 0 is supposed to be. Let me bring that up. Okay, 0, cross section station 0 will be 0, 10, 10, 5, 35, 5, and 45, 10.
I think that's what I think they're going backwards as well. The 0 was and the 1,000 was the
So-
other.
Mm-hmm. Okay, so close that, and then bring up the cross-section window again, and let's see what it did. If we step between them, so this is at 1,000, if we move downstream, you can see it's gradually getting wider.
Work. Close it.
Yeah, I think it's good.
So that should be good.
Click apply. No, on the left it should be 10.
Oh.
The elevation on that other side needs to be 10. Click apply data. All right. And then make the right bank equal to 10. Okay, you're doing the rectangular one, right? Not the, or is it you doing the trapezoidal?
0, trapezoidal. That's the one you're.
Okay, yeah, I'm sorry. 45 was right.
Okay.
Yeah, 45.
It still looks skewed, don't it?
Yeah, apply that data. Okay. All right. Now, close that. Actually, no. Let's take a look at 1,000. Okay, so we're going to have to change 1,000 as well. I think we got them flipped.
I think it did too.
So let me go to the rectangular one. I'll bring it up so you can copy. So what we're doing here is just assigning a coordinate system to the cross section.
It's the, oh, okay. That's it.
All right. So we have a channel. We need to send some water through it. All the computer knows so far is think about this is like a bowl that the water is traveling through, or like a gutter or a funnel of some sort. We have to define the flow rate that's going through there. So we can close these two windows, and we're going to do a steady state run. And so it's the one that's right next to the geometric data here. View/edit, steady flow data. And we're only going to do a single flow rate simulation. So here where it says 1, that's plenty, because we want to find out 1,000 CFS. And so here, the thing we need to enter, PF, we're going to put in the profile. We want to find out what's the depth when the flow rate is 1,000 CFS. And by the way, down here at the bottom, it's always giving you hints about what you should be entering in the units.
For the profiles.
Okay, so 1,000, and then we also need to define the boundary conditions, because we haven't told it yet what the water depth is where we know the situation at location 1. So click on boundary reach conditions, and what we know is a known water surface. So click on known water surface, and the known water surface is 10. Wait, did we start at 0? Yeah, okay, so then we need to say 5, because you know, we were using our elevations as 0. Okay, I'm worried all of a sudden that maybe I've done the profiles wrong. Let's double check the coordinates on. Let's go back to the reach and let's look at the cross sections. 7, and then okay, 5. Yeah, it's good. It's good. I was worried we'd gone down to 0. All right, so where we're at, we told it that we know the depth at location 1, so it's a known water surface, and the depth there, it's 5 feet of depth, but it's actually 10 because it's above the channel. So if the depth is 5, then the water surface is 10 at location 1. Okay, so put in 10, click OK, OK, and then apply data. Upstream, we don't know the boundary condition. That's what we're solving for. Okay. And then we do the run. So steady flow analysis. So under the run menu here, steady flow analysis, subcritical flow, which we already determined from the Froude number, and click compute. And it does a little bit of thinking and it finishes. All right. And then what we can do is we can look at the results in a graphical way. So view XYZ perspective plots is an interesting way to start looking at it because it kind of allows you to rotate through. And so have a look at the screen as I'm rotating. You can see upstream is here. Here's the downstream section. And so it started where it was full to the top of that trapezoid. And now remember, we made this really tall. We made it 10 feet so that it didn't spill out of the side. But let's actually take a look at the cross sections and see view cross sections. This will show you how deep the water is at any location you want. So we're starting at our trapezoid. So this is at location 1. We already knew the depth was 5, so that's correct. But then let's scroll all the way up to location 1,000. And it's saying that the water depth, if I make that a little bit bigger, the water depth is between 14 and 15. And what had we calculated when we did it this way? It said that the updated water surface would be 15. But this is more accurate because it divided it up into 10 slices instead of a single slice. And so it's kind of accounting for the energy losses in a more accurate way than when we just jumped all the way from section 1 to section 2. All right, you've really been drinking from the fire hose tonight. Probably you'd never done the standard step method before. So you learned both the manual way to do it and the automated way to do it. Of course, I'm recording this video, and so you need to practice it. It's not going to make any sense unless you practice this. And honestly, I'm not that good at HEC-RAS. HEC-RAS isn't like in my main core area of expertise. And so because of that, because I only use it like twice a year, I always forget. I have to reteach myself every 6 months how to do this. And so my suggestion is that after class, work through this example again before you start on the homework. And let's take a look at the homework just so you get a sense of what I'm asking. Okay, here's the homework scenario. I'm giving you a break because both upstream and downstream it's rectangular. So the geometry isn't transitioning to a trapezoid. But I ask you to consider this channel where we put in an obstruction that's choking the flow. And so we know the depth. We can measure the depth at a certain location. The measured depth is 3.8 meters. By the way, meters. So you can change the units on HEC-RAS over here under Options, Unit System. So on the homework, you need to switch over to SI. All right, so in this example, what we have is a situation where we want to find out two things. Number one, what is the depth if you go 1,500 meters upstream? And then the other question is, how far do you have to go upstream until you find a depth of 1.207 meters? So you can solve that with the spreadsheet and get the answer, and then double check the answer with HEC-RAS. Or you can go straight to HEC-RAS, because that's really what today's module is all about, is HEC-RAS itself. So as I'm indicating, it's getting less deep upstream. So this is again subcritical flow. I don't tell you the Z's, and so you're just going to have to assume some datum I mean, that could be that the datum is 0 at the downstream section. But what I am telling you is the slope of the channel and then the distances that we're interested in. So my suggestion is to use 100-meter cross-section spacing as you're working upstream. And let me give you the handout that has these. I thought I printed out 2. Oh, yeah. Here we go. So here's the homework assignment. At first glance, do you have any questions as you look at this assignment? Just the one question, because I'd like you to use your time as far as the homework goes. Number 1, solve this example that we just did in class. Solve it a second time. And then I think the method will maybe be crystallized in your mind well enough that you can move on to this unfamiliar one. And if you want to email me before you submit the assignment on MU Online, if you want to check your answers, I'll tell you if you've done it right, or if you still maybe need to keep looking.
What if you want to ask the question about storm card, because I didn't get it at all?
I'd be happy to have you come by my office. Yeah, stop by. I have lots of office hours each week. And if my office hours don't work for you, then we can make an appointment.
So does it mean that every class we're going to learn a new software?
No.
The reason why I ask is because I still try to get my head around HYA, storm card, and another one came in. So.
How many classes are you taking this semester?
4.
4? So if you have 4 classes and you assume the standard 40 hours per week, that means you should be spending 10 hours per week studying in this class. And I think 10 hours per week is enough.
No.
I do. I think so. Yeah.
I think I need more.
Well, just less sleep then, right? Less video games? I don't know. Less work? Okay. Well, yeah, if you have questions, come see me, because if maybe you have some stumbling block and it confuses you for hours after hours after hours, come see me and then we'll fix it very quickly. All right. That's all for today. We didn't even get a break tonight.
It's better.
Yeah, we went straight through. So remember that this homework assignment, homework 4, that's due on Wednesday of next week. And if you have questions, let me know. Thank you.
Okay.
That video will be posted